So now we want to give you an introduction to the tracker software, and you will need a 32-bit Java virtual machine or 32-bit VM to run tracker. So if you're experiencing problems with installation, then that is likely the issue is your Java. All right, but once you get that cleared up and once you get it downloaded and get it running, you click on it and it opens, and this is what you see. And to open up a file, you just hit the folder button, and your 3 movies are, of course, in your lab folder, so you can download those, and those will probably be in your download folders. I have the video stored in Google Drive on my machine, so I'm going to open up the golf ball movie, and when you open it, this is what it will do. It'll load all of the frames, and there should be roughly 240 frames or so, maybe 243 if I remember correctly. And it should load. Here we go. All right, so once it opens, this is what the interface looks like, and you'll note this slider down here, and can slide, and this is literally dragging the frames throughout the entire video. So when you click and drag, it will drag each frame, and you can see what's happening. Now, the video real time is only a second long, all right? But in slow motion at 240 frames per second, it's several seconds long. And so the actual dropping of the ball does not occur until about frame 150 to 155 or so, okay? So what we can do to not have to click through every single frame here is click this button, which is the clip settings, and this will allow us to designate what frame we want to start our analyzation process at and the step size. All right, so I'm going to start analyzing at frame 155. All right, and instead of stepping through one frame, I'm going to let it step through 4 frames. And this will give the golf ball time to appreciably move in between each measurement, especially at the beginning up here. If we were to only go through it frame by frame, the golf ball really would not move significantly, and your data may look quite messy. So I'm going to start at frame 155, go through a step size of 4, and when I do that, and I click out of that box, if this frame were not the automatic end frame, then it would automatically adjust to the nearest multiple of 4 from 155. All right. So if your end frame number changes or you use a different start frame or a different step size, and then the end frame automatically adjusts, it's going to adjust so that it ends automatically on a frame. And since this is slow motion, the frame rate is actually 240 frames per second. And then when you click OK here, you'll notice the frame rate will change, okay? So the next thing we need to do is to tell Tracker what scale or what size our frame is. So to do that, you click on this button, and when you do so, it'll come up with this new, and we want to choose the calibration stick. So choose a new calibration stick. Now, the calibration is to 100, and it's saying that it wants you to designate something that's 100 centimeters. Well, we don't have something that's 100 centimeters. We have something that's 50 centimeters. So what we're going to do is click and drag the calibration stick across these 2 black pieces of tape, and those are 50 meters apart. So to change our 100, just click in this box, hover over the 100 with your mouse, click in the box, and then change it to 50, and hit enter, and now the system knows that this is centimeters. All right. The last thing we want to do is designate a coordinate axis, and to do that, hit this button, and this X and Y axis will appear, and the origin is right here, and you can click and drag the origin around. It will likely be beneficial to put the origin right over the golf ball. Okay. Now, one last thing we want to do before we actually start taking measurements is notice that the frame, the camera was tilted just a little bit, so the golf ball isn't going to fall directly along the x-axis here. So I'm going to tilt the x-axis just a little bit so that way the golf ball falls directly along the x-axis, and that'll allow us to only need our x-axis data. All right, that will allow us to only want our x-axis data. And by the way, you can click forward through your frames using this button, and it will click through every 4 frames. You can click back every 4 frames here, or you can go back to your original designated starting point by clicking here. All right. Now we are actually ready to take our measurements, and I'm going to hit create and point mass. And this tells Tracker that I'm going to be tracking a single mass. All right. In our case, the mass is the golf ball. And you'll notice this chart pops up, and now we have a table over here with time, X positions, and Y positions. So as we click through this, you'll see this data fill in, and this chart will also fill in. So now you're ready to actually collect data, so we just hit the shift button, and when you do, you'll notice that your cursor is now a square, and every time you click on the golf ball, it's going to record a measurement and then advance the frame. So now we keep holding the shift button down, and we're just going to click on the golf ball and follow it through all of these frames. All right. And you'll notice that our graph is already starting to look somewhat like a parabola. And you'll remember that I've said before, we don't want to choose polynomials, if we can help it, unless we have a good theoretical reason. And in this case, and I'll show you why in a moment, we actually have reason to fit this data set with a polynomial. All right, we have a good reason to fit this data set with a polynomial. And the reason being, right, the reason being is that the theory predicts under constant acceleration, the position versus time should be a polynomial. And I'll show you that equation here in just a minute. And so we get this nice polynomial here. And I'm going to use this as my last frame because now I'm getting to the point where the golf ball is getting down toward the table, and I can't tell right now if the golf ball has actually hit the table or not. So I'm just going to take these 20 data, and I would encourage you to take roughly 20 or so data points as well. Now, to actually analyze the data, all right, to actually analyze the data, what we can do is click in this time column, drag over to the X column, and now you'll see both columns are highlighted, and just drag down. And so now the time and the X column are highlighted, and if I hit Control C, then that will copy that data, and I can open up a blank Excel sheet and click in cell A1 and Control V, and now my data is copy and pasted. Now I'm going to do a couple things. You'll note that everything is in scientific notation. All right, you'll note that everything is in scientific notation, and that the mass is labeled as mass A. Right, so you can measure multiple masses: mass A, mass B, mass C, whatever. But since this is particularly a golf ball, I'm just going to rename this golf ball. All right, so that way we know that this was data attached to the golf ball. Secondly, I'm going to highlight both columns, and I'm going to format the cells to just be general. Okay, I'm just going to format these cells to be a general time. Or I'm sorry, let's do it so that we carry 4 decimal places. Let's do general. I apologize for being wishy-washy here. Let's just do general. So now I have my data, all right? And notice that Tracker will take this out to several decimal places, all right? So really, in truth, there's no way that Tracker can actually be that accurate, but for the moment, we will keep the data as is. In reality, what you would do is trim off these decimal places to maybe about 2 or 3 decimal places and attach some sort of uncertainty to those. But for the moment, all I'm really interested in is what this position versus time data looks like. And you'll see that this looks like a parabola. Now, as I said before, why should it be a parabola? Well, the equation that governs position and time under constant acceleration, and in this case our acceleration is free fall or gravity, my equation is equal to 1/2 times gt squared plus vit plus my initial position. So my g is my acceleration, vi is the initial velocity that the object has when I start taking measurements, and yi is its initial position. And all of this is again with respect to the origin. The most important piece, I should reiterate, the most important piece is going to be this 1/2 g. This is the coefficient on your squared term. So now when I hover over a data point, add trend line, and I want to choose the polynomial option, right? Polynomial or 2, and I go down here to display equation on chart and the r squared value. Now look at that r squared value. That is a really nice r squared value, right? And our leading coefficient is 501.79. Now this is in centimeters per second squared. So to get this into meters, I would need to divide by 100. So my leading coefficient, all right, my leading coefficient right, is going to be 5.02. All right, if I round, then it's going to be 5.02. And what exactly does that mean? Well, that means that that represents 1/2 of g. Okay, 1/2 of g. So to actually get g, to get a value for g, we're going to multiply that number by 2. And we come up with 10.04. Now remember, the accepted value of g is 9.8, right? 9.81 to be specific. And we're measuring 10.4. Really, that's not bad. 9.8 versus 10.4, that 10.04 rather, that's really quite close. So I'm pretty happy with that. Now a second way to get the measurement is actually going to be to look at the slope through each individual data point. And if I want to get the slope, say I have 3 data points and I want to get the slope on the middle data point, the slope through that data point is equal to the rise through that data point divided by the run. And one way to estimate that is to take the rise between the before, the point after our point in consideration and the point before our point in consideration and find the difference between those two. That will give me the rise. And if I take the difference between their times, that will give me the run. Right? That wasn't written very well. That will give me the run. So what I'm going to do is take this y position and subtract this y position, and that will give me the rise. And I'm going to take the difference in their times, and that'll give me the run, and that will give me a slope, approximately the slope through that point. Now, in formula form, in Excel, what this is going to look like, and note that I'm going to have to start with the second data point because I have to take the point before and after. And if I start at my first point, there is no before point to take into consideration. So I'm going to hit equals, parenthesis, the position after, subtracting the position before, and then do the same thing with the times. And this gives me a rise over run estimate. And then I click and I can only take to the point right after or before the end, because again there's no point after here for the formula to work with. So now if I plot this data, I should come up with a linear line, or very close to it. And the slope of this linear line should be my acceleration. And notice how close that value is to our acceleration from before, but now we're doing it with a linear line. And so Again, you'd want to move the decimal places 2 points over because this is in centimeters and we want it in meters. So in this case, we're measuring our acceleration to be 10.0